Recording. Okay. All right, good. Sorry about that. Okay, so I was saying that the first tutorial is now online. It has instructions to help you set up your local development environment. Also, instructions so that you can check that everything works as expected. Please give it a go this week, as next week is when we start the labs. We sort of expect you to have these things, at least to some good working order by then. If not, there will be time next week to look into it, but better do it this week. With that said, now there is a screen. There you go. So with that said, did you do your pre-session reading? Let me see. Several things popped up in Slido. Extend the quiz time. Okay. Sure, I'll see what I can do. I mean, to be honest, the quiz is supposed to take you only a few minutes. Typically, we would do it like right now. So we would stop the lecture, like pause for a few minutes, do the quiz, and then continue with the lecture. But given how everything has gone wrong at the beginning of this lecture, I'll extend the time for these ones. And starting next week, hopefully we will be able to begin on time and without that many interruptions. And in that case, we would have the quiz at the beginning of the lecture. Okay. All right. A couple of people asked me to explain the journal and how it's replayed and so on, and we will go over that as part of the lecture anyway. Okay. The quiz is indeed based on the pre-reading material. Yes. Okay. So the quiz is open now. It's open until I think 2 p.m., but I can extend that to later today until, let's say, probably end of play, like 5 p.m. today. Hope that works for everybody. But as I said, starting next week, we'll try to do it properly and only have the quiz in the first few minutes of the lecture. Okay, so with that said, then is the quiz worth credit? Yes. This was covered last week. So all of the quizzes, so every lecture will have one of these quizzes at the beginning. And all of the quizzes together across all lectures count towards 5% of your final mark. And yes, the quiz is graded and it does contain topics from the pre-session reading material. Okay, here's what we'll do. This one, right? Just this one. I will extend, as I said, the quiz to 5 p.m. today. Yes, you can take the whole time to do the quiz. And to be honest, if you do it this time, it would probably be easier for you because we will be answering those questions as we go. But again, starting next time, we will do it properly. So the quiz will be open just for 10 minutes at the beginning of the lecture. We'll do the quiz, and then we will close the quiz and begin the lecture. Okay, guys? So with the quiz extended, I mean, I'll do it as soon as we do a break. Let's move on with the rest of the lecture for today, and discuss the quiz again later. Okay, right. So we've said in the past that we want to understand what are the design decisions behind all of these big data systems. So let's start with like painting the scene, right? So we go back like 20 years now. back to when Google was downloading and indexing the web. So what do you need if that is your business, right? You need a lot of machines, of course. You need parallelism. And what you would do is you would have those machines running crawlers, and that is, software that would go out to the web, download a web page, store it somewhere, parse it, identify links, and then follow those links to download more web pages, and do this recursively until you either have gone a certain number of hops away, or you run out of links to follow. Right. There's some questions on Slido about weightage of marks. This was all in last week's lecture notes. If anything is unclear there, please let me know and I'll clarify. Okay, back to business. So you have these like probably thousands of machines downloading the web, and you want to be able to store it somewhere. So that somewhere needs to be able to withstand a large rate of data being stored on it. But then you also want to do something with the data you've downloaded and stored, right? You want to index it. So how do you then go and load the data, right? These are the two main questions we need to answer, but keep in mind what the use case is, right? The use case is that of aggregating or gathering a large volume of data in a possibly small amount of time, and then going over all of that data to build an index so that you can then query the index and get the data you want. Okay. The first thing that comes to mind when it comes to storing stuff is a file system, right? That's the most basic storage abstraction people are exposed to when they are working on the computer. So what would one expect of a file system? Typically, a file system offers you namespace, so it gives you a way of naming your files and organizing them somehow, right? But we're used to file systems that have directories in a hierarchy. So you have, a root directory. Every directory then has either a number of directories or a number of files, and this is all in a tree, in a tree structure. That's not the only options, of course, right? So that there are file systems out there that completely forego this tree hierarchy and they go for a graph. There are file systems where directories are not really a thing. You have files with names, and then you assign tags to your files. But in the general case, without loss of generality, we can assume that we have this abstraction of a namespace, names for files, and then some way of navigating to those files. You also expect the file system to define a storage format, and that is exactly how the data will be stored on whatever medium you use to store it. You then need a mapping from the file names to the storage, and finally, you need read and write access paths and an API implementation. So going from like the highest level of abstraction to the lowest, you need a namespace, a mapping from the namespace to a storage, the storage itself, and then APIs or ways that you can go from top to bottom and back up again. Right. One observation one would make if they were to look into different file systems would be that most file systems store data in blocks. Why do you think that is? Any ideas? Please feel free to type in Slido. right? Easy to retrieve, can control size and also hash them, can be read quickly in chunks. Yep, all of these make sense. Yes. I'll pull out two bits in from these answers. The first one is this mention of chunks. Typically, you store your data on a disk, right? Disks are structured in blocks. The block size changes, and the definition of what a block is changes depending on what type of disk you have. So on a rotational disk, the block is a part of a cylinder. In a solid state drive, the block is part of a flash chip. In a non-volatile RAM, the block is, again, something different. But the storage is almost always structured in blocks. So it makes sense for whatever you layer on top of that to also use an abstraction of blocks. And you would do that so that you can gather together several blocks of the storage, and then that would be a block of your file system. There are other reasons why you would do it so. And the other reasons are, someone says easier to read and write. I'll rephrase that and say it's easier to, easier to retrieve. Someone has actually said this. So it's a way of indexing your information. And an analogy I like to use is that of, if you've ever moved houses, you know how you put stuff in boxes. It's much easier to transfer your stuff when it's in boxes, and if you've done a good job of indexing your boxes, like only putting things that belong together in the same box, and then keeping track of like box numbers and what is in each box. It's much easier to then go and find stuff, as opposed to just putting everything in one big pile. Yeah. So these are the two key reasons. One is that somehow, to some extent, this abstraction of a block is imposed by the storage. The second main reason is retrieval. You want to have an easy and fast way of going to your data. If we didn't have the data in blocks, the data would be stored how? Like all over the disk, and then you would need to index morsels of data. That would be much harder. And then all of the implementation on top of that would be much more complicated, as opposed to here is an index of disks. Compare that to here is an index of everything on the disk, right? Okay. Exactly, as someone says, blocks are implicit indexing available in the file system. Yeah. Okay. So why should we bother with a distributed file system then? And why don't we always use a distributed file system? These are two questions we should have answered by the end of this lecture. So when is a centralized file system not a good enough option? There is an easy answer here, and that is when your data cannot fit in a single centralized file system, right? But someone mentioned something about going parallel. And when you have an infrastructure consisting of like 10,000 computing nodes, then it makes sense to try and also distribute your file system. So in cases like this, the distributed file system seems like the only way forward. Why don't we always use a distributed file system though? So when would the centralized file system be the best option? So this is the flip side, right? If you can fit your working set in a single machine, and you can process your working set with whatever resources you have in that single machine, then why not do it? Because when you go distributed, you need to keep track of many things. You need to solve way more difficult and more numerous problems, as we will see shortly, right? But for the use case that we are discussing, where you have a very large number of machines doing stuff in parallel, having a distributed storage is well, makes sense. Yeah. Yes, and as someone says on Slido, this also helps with they say redundancy. I'll say fault tolerance. We said last time that faults, errors in an infrastructure that is so big are the norm. They're not an exception. So you want something that is distributed because that gives you this level of redundancy that can help with fault tolerance, but can make availability much harder. We will discuss all of this. So what is in a distributed file system? Right? What are its basic components, and what does its architecture look like? So many fish in the ocean here, many distributed file systems around. Distributed file systems have been developed since networks were a thing. But let's have a look at what happens with file systems designed for a use case like the one we're discussing, right? So the main components are your distributed backend and then a client-side library. The distributed backend offers you a storage layer, and that is the part of the file system that decides how to store what and where. And then there is an access layer that gives you basic indexing and retrieval functionality. This is your mapping from names or whatever to your data that is stored. Both of these layers need to be scalable and need to be fault tolerant, need to be reliable, need to be load balanced, and so on and so forth. And we will see how storage and access are, how they achieve these options, these properties for GoogleFS and HDFS. But then what happens with access control, and what happens with consistency and concurrency? All of these are things one needs to keep in mind when they design a storage layer and an access layer. And then, as I said earlier, you have the client-side library, and that is what your clients, of course, use. And this will provide a familiar API. So you don't want to surprise your users, let's say that. So if users are familiar with the API of, say, going through files with the Java standard library, then you want your client-side library to follow that abstraction more or less, so that people are used to opening a file, maybe seeking, reading, writing, closing a file. That's the kind of API you want to offer. And this API and this client-side library will hide away all of the implementation details, and there's quite a few of these. Typically, what will happen is that this client-side library will have some memory allocated to it on the client side. It will be caching information there. It will be batching calls to the distributed storage. And every now and then, it will be communicating with the backend through some sort of remote procedure call. The question there is whether blockchain is an example of a distributed file system. Blockchain is a rather weird beast, because the operation of blockchain is distributed. Blockchain itself, not necessarily. Depends on exactly how you model the whole problem, but I'll just leave it at that. I don't want to get into the whole blockchain discussion live in this lecture, but if this is something that interests you, please feel free to post a question on the Moodle forum. Yeah. Yeah. Okay. So as I said, there are many network file systems out there: NFS, AFS, CODA, AndreUFS, you name it. What is wrong with these file systems? So why do we need yet another file system? So pretty much all of the pre-existing file systems were designed for different use cases. For example, NFS is used to this day. It's a way of Unix servers exposing part of their file system for other nodes to access. NFS strives to offer like access control and is designed for read-write scenarios, like accessing your NFS files as if they were your local files. That's not exactly what we want to do here, no. We want, remember, this file system to be a very fast data sync, so we can push a lot of data to it. And then we want to go in and scan over all of the data that is stored there. So NFS is not really what we're going for. A couple of questions, I'll get to them in a minute. Similarly, for CIFS, AFS code, all of these file systems are designed for a different use case. And for many of these file systems, fault tolerance and scaling was not even part of the blueprint. So for NFS, for example, if your server exposes part of its file system, like exports some directories as an NFS drive, and someone else mounts it, and your server dies, the data is gone. There is no provision for fault tolerance and things like that. Other file systems have introduced mechanisms for that, but it seemed like when Google was going through this process that none of the existing options would cut it, so they needed something new. Right. So let me go through the questions that were asked in Slido. So so this again about weightage. Yes, someone asks, what is the weightage of quizzes? Examination is 75%, quizzes are 5%, and coursework assessed exercise is 20%. Yeah. Okay. So it's part of coursework, not a part of exam. Quiz will be open until 5. So right now it appears as being open until 3. No, until 2, I think. Can't remember. I'll extend that until 5 p.m. So here's a technical question. DFS has 2 things: storage and processing. Are we looking only storage aspect right now in the slide? And I think you mean this slide. It's a little bit of both. I'm not sure what you mean by processing for a distributed file system, because the file system, what it does is it stores data. The file system itself will not process data, right? It will give you access to the data so that you can process it elsewhere, but the file system itself is not processing anything. So let's take now a step back here, right? So again, let's think about this use case. Suppose you have 10,000 workers. This can be 10,000 computers, or it can be 10,000 processes, like a large number of concurrent things downloading and storing the web on a DFS in order to then index it and query it. Yeah. So here's a question for you. What is the most important quality or characteristic of a distributed file system that is to be used for storing and indexing the web? So if you go on Slido, you should see a poll right now being open for exactly this question. So yeah, people are answering that already as far as I can see. So I'll just give you maybe 1 minute to input your view. Mm-hmm. Okay. So I'll just leave it this for maybe 10 more seconds and then close the quiz. Andrew here asks whether we will cover data lakes and lake houses in this course. We could do it as part of the in that week 9 lecture. Typically, no. What is a data lake or a lake house, right? The typical definition of a data lake is a shared storage distributed infrastructure. And most of the things that we see are shared nothing. We could discuss data lake issues later on. Let me see. I mean, we will run a poll later in the semester to decide what we'll do with 9. So if you can remind me by then, I could make this an option. Okay, so I'll stop the poll. Let me see. Can you see the results? Can you see the? Can you guys see the results? I don't even know.
Yes.
Yes. Okay. Good. So you'll see how most people have gone for scalability. Fault tolerance and latency come like second and third, and throughput is at the very end. Right. So here's my take on this question, and we can discuss this, of course. I think that out of the 3 things mentioned there, of course, this was somewhat of a trick question, right? Latency is the only thing that is not important, because both of the cases, both of the scenarios we discussed, like storing the web and then index the web, so scanning through it, are not latency sensitive. You definitely need the file system to offer you throughput, both for reads and for writes. And since this is distributed, you definitely want it to offer fault tolerance and scalability. But we can discuss these 3 properties and try and come up with which one is the most important one. I would say that for a use case like this, perhaps fault tolerance is not that important, because if something goes wrong, you can always go and re-download stuff from the web. And no matter what you do, the web will probably change so quickly under your feed that by the time you are done indexing, your index is already outdated, right? Still, you don't want to do that all the time. So some level of fault tolerance is required. Scalability for sure, and throughput for sure. So I would rank these 2 as very, very important. Let me see. Okay. Can I please ask that people only post questions and comments on Slido, because going between Slido and Zoom chat is a bit clunky. Right. Okay. So again, a quick intermission here, because there are some things that not everybody really understands. If you have a system consisting of like 10,000 nodes, how do you connect them? You can't have a switch that has 10,000 ports, right? No such thing exists. So what you need to do is you need to have some kind of topology. Typically, I mean, you may have seen photos of what a data center looks like on the inside, right? You have these cabinets, rack cabinets, and in these cabinets you go and you put your servers there. Yeah. Oh, okay. Okay. Someone said on Slido that you also need to go between Zoom and Slido right now. Yes, that's point taken. But anyway, it would help me a lot if you could just use Slido and not Zoom and Slide, right? If it's possible, sure. Someone else says, doesn't throughput affect latency? That can be a long discussion. You could have a system that offers high throughput, but not such high latency, or high throughput and relatively low latency. But there is some link between the two. It's not, throughput affects latency, or actually designing a system for high throughput means you've made some decisions that may lead into having lower latency. But it's not an always happens case. Okay, so back to this topology, right? So you have your cabinets, your racks in the cabinet, and usually in every such cabinet or rack, you have a switch called top of rack switch, or TOR, as you see in the picture. So all of the servers in this rack connect to the top of rack switch, and then all of the top of rack switches connect to multiple switches at an aggregation layer, and these connect to possibly multiple routers at the core layer, and from there to the internet. Yeah. What this means, though, is that there is this notion of a distance that now makes sense in this setting. Nodes that are in the same rack are closer to each other than nodes in separate racks. So the bandwidth you have available for your communication is probably greater. The latency is lower because you have fewer network hops to go through. Because otherwise, if you need to go outside your rack, your packets will need to go through several of these hops. So you will, if you, what's my pointer? Hello, pointer. Oh. Oh. Okay, this. Hope you can see my my mouse, because this does not want to cooperate today. Okay, so for a server in here to communicate with like the server on top of it, your network packets will go from the server to the top of rack switch and then to your neighbor, right? If you want to talk from here, someone over here, your packets will need to go from your server to the top of rack switch, from there to some switch in the aggregation layer, and then possibly further up the hierarchy, and then down again until you reach the server. Yeah. So this takes more time, hence the latency is higher. And since you're going through all of these intermediate layers, there is a possibility that the bandwidth you will have available will be lower, because it would be shared across more entities. Now, typically, if you do this correctly, as you go up, the bandwidth available also goes up. But there is a level, and there is a limit to how much bandwidth you can have available at any layer. So this model here still holds, right? So here's a quick question: how can we know where is each node located, and what is the distance between any two nodes? You would want to be able to tell this, like know where each node is located, because at some point you will need to choose among multiple nodes, and you probably want to choose some node that is closer to you than some node that is further away from you. But what information do you have? You probably just have like an IP address. Why is this turning into a networks lecture? Because networks are a key component of distributed systems. So we need to at least cover some of this. Yeah, we won't go any deeper than this, by the way. So how can you know where each node is located? Several options. Some people would use special names for their nodes, such as it's like rack name dash server name or something like that. That can become problematic if you move things around. If you like take a server from one rack, move it in another rack, you will have to change the server's name. You could have sort of a central directory service that tells you exactly where each of these servers is located. That works. But since we don't have like millions of nodes here, we're talking like thousands, it's not unheard of to just store a file on each server with the location of everything else. And then that file can be downloaded from somewhere every now and then so that you get the updates. Yeah, all of the options that people mention in Slido make sense. So rack, shelf, slot, port, address. Yep, but you would need to change that when you move things around. And so if one of your servers has decided to store something on some other server and has stored a mapping to that data item, and you move the remote server, you will need to go around your system and update all of those pointers. A central address table, a central directory of where everything lives, is probably a better way to do it. And if you don't want to have that central directory as a single point of contention, like a bottleneck, what you would do is you would replicate this information on all your servers. So this is what we're going for. Okay. Good. So back to HDFS land or Google FS land. This guy is designed to operate over a cluster of commodity machines. And here commodity, I mean, the definition of commodity is a bit vague. Commodity machines are supposed to be off the shelf, so inexpensive and possibly unreliable. Now, if you walk into a data center, you won't see like run-of-the-mill computers there. You will see blades with probably like redundant power units and what have you. So off the shelf is quotes. Regardless, though, I mean, these are fairly inexpensive machines for some definition of inexpensive. HDFS has two main backend entity types. It has a name node and it has data nodes. The name node is this single guy, single mastermind that provides directory service and metadata storage. And the data nodes are where the data is actually stored. And these two guys, they practically map one-to-one to the two services we said earlier that you expect a distributed file system to give you, right? Like data storage and a way of getting to that data. And then you have your distributed, your HDFS clients, which is just clients, like client programs, user programs using the HDFS client library. With HDFS and Google FS, all of the communication is over TCP/IP. The reason is that you sort of rely on the communication medium being reliable, and you do that so that you don't need to worry about packets going, being lost without you knowing and without the system itself doing something about it. Given that this is designed for a use case where you, as we said earlier, you want to store with high throughput and then scan with high throughput, this is designed for write once, read many access. So the files you will store on this file system will never change, right? I mean, they can change, but the design here is that let's assume they never change. Why? Because again, think of the use case. I'm downloading a web page, right? In that point in time, that is the state of the web page, and the web page itself will not change. If I go back later on and re-download that same web page, the data might have changed, but that's a different version of that web page, right? So the data I have stored is practically immutable. So write once. But that data you will go and read multiple times. There's a very good question, what happens if in the case of the name node crashing? Hopefully we'll cover that today, okay? The answer to the question is in the, should be in the paper, in the pre-reading material. But let's see whether we manage to get to that point. And HDFS is designed to provide then this high throughput batch storage and processing, high availability, fault tolerance, and to be scalable and elastic. Now, we will try to break this down, right? What high throughput means, what high availability and fault tolerance means, and how it's achieved, and what scalability and elasticity means. Okay, works on my thing there. So how can we accomplish high availability? Typically, what you do is you take your data, first you partition it in blocks. And why do you partition it in blocks? For similar reasons like the like the ones we discussed earlier for the file system, right? So you partition it in blocks because that allows you to manage your information in blocks as opposed to like bytes. So if you decide to do something with a part of the file, you will do that for the whole block. Here's one of the things you can do. You can have a per block checksum. Why do you need a per block checksum? Because things might go wrong. You could store something on a node and the node might have a faulty disk, or the data might have been corrupted while in transit, or many things could happen. Having a checksum next to your block allows you to then go and compute the checksum on the block, look at the stored checksum, and see whether everything agrees. Once now you have your data partitioned in these blocks, what you will do then is you will replicate it. And replication will be on a block basis. So for every block, you will go and create additional copies of that block somewhere in this distributed system, right? Why do you want these replicas? Well, as we will see, I mean, the main design decision is you want multiple copies, because if one of those copies fails for whatever reason, you have more versions of this information, more copies around to survive that failure. But with replicas come extra worries. Like, so you need to have a mechanism to check for liveness, to check that your replicas are available and correct. And in case something goes wrong, you need to have mechanisms to repair, right? So if, for example, I have a block and I need the block to have 3 instances, like 3 replicas of the block, I need to go over now and then and check that all 3 of the replicas are there and all 3 of the replicas are correct. If I have fewer replicas, I need to proactively go and create more. If some of the replicas have failed the checksum test, I need to throw them out and then go and create more, and so on and so forth. And then these replicas need to be placed carefully. What do we mean by carefully? So let's see. We will discuss this in more depth shortly. We said we need high throughput for HDFS. So high throughput is in the write path and also in the read path. How can we accomplish high write throughput? And how can we accomplish high read throughput? So typically, you do this by avoiding touching the disk as much as possible, okay? And if you can't avoid it, then avoid random IO as much as possible. For those of you who have taken IDSS, you may remember how we were discussing this. But even if you didn't, here's the quick version. Sequential IO is always faster than random IO. Probably everybody knows that. What is quite interesting is that sequential IO on old school disks, like rotational disks, is still faster than random IO, or can be faster than random IO on faster disks like SSDs. And even in RAM where you don't have things like moving around, you don't have a rotational device and so on, sequential IO is always much faster than random IO. Okay, there is of course a reason behind that, and we can discuss the reason, but I mean, let's do it on the forum, right? Why even in RAM that is the case. So we want to avoid random IO like the plague, but even better, we want to avoid touching the disk if we can. Okay, but how is this possible? How can we avoid touching the disk? How can we avoid random IO? Any ideas? What exactly is throughput, someone asks. Throughput is the rate at which you can complete operations. Right? Store things in RAM, caching, yeah. So by caching as much as you can and caching aggressively, you can avoid touching the disk. Right. When you can't avoid it though, you need to avoid random IO. How can you avoid random IO? Someone says store related data together, hence access sequential. Indexing. Okay, I mean, there's a few good suggestions there. Use blocks and indexing, priority pipeline, restrict IO. I mean, I'll pull out bits from all of these answers. BB plus trace, yes. So it's probably, I mean, all of those ideas are have merit, okay? But there is something we need to like take a step back and think about. Avoiding random IO. When would we actually do random IO? We would do random IO possibly on the read side when we go in and read the data in. But if our algorithm scans through all of the data anyway, we probably don't do much random IO. Okay, so perhaps random IO on the read side is not that big of a deal. But how about writing? So avoiding random IO in writing practically means that our model will only ever go and append stuff to a file. We'll never go in the middle of a file and change something. We'll always append. So can we come up with a design where reads scan through the whole file sequentially and writes only append? And if we can come up with this design, how would it work for arbitrary cases? Yeah. So caching for reads is definitely an idea there. That would avoid touching the disk, and buffering for writes would avoid touching the disk for writes that many times. But the random IO needs some further thinking, right? Then what about durability? Oh, let me step back. Someone says, isn't that just a linked list? It could be seen as a linked list of what though, right? So if we're talking block level, yes, your blocks are one after the other. It's not necessarily, it doesn't have to be a linked list. It's just that they are one after the other. So if you remember from database courses in IDSS, if what you're going for is the linked allocation of blocks, you could have the same effect with like the index node too. The key point is you always want to append. So even if you have just one block, even if your file is just the one block, you wouldn't, and you want to add more stuff to it, you wouldn't go and add a new block and then add your information there. You would keep adding to that same block until it's full, but only at the end, like append, right? So what happens then with durability, right? Durability becomes a problem because if you buffer your writes, meaning if you store your writes in main memory until some buffer fills up, and then you write it on disk, then what happens if your system crashes while that buffer is filling up? There is a trick here that was borrowed from the database world, and that is the write-ahead log. So what is a write-ahead log? The key idea is this: whenever a change comes into the system, like something that needs something new that needs to be written, or something old that needs to be changed, you first append that information, the fact that this thing needs to be changed and how it needs to be changed, in a log. This is the write-ahead log. You add it to the log, and then you flash the log, you store whatever is in the log on disk. And when that is finished, only then you go and apply the change to your in-memory image. Okay. So what gives though, right? Because now we are touching this. The fact that we append this data to the log means we don't do random IO on the log. Excellent, right? But I just said that we need to store that log on disk before we go and do the buffering of the write in main memory. So how is this a better option? And this is a subtle point here. There is this trick, again, coming from databases, called delayed commit or group commit. Okay, so what happens here is that as changes come into the system, you go and append those changes to the log. You don't acknowledge to your client that the change is complete until after that log has been flashed on disk. So what happens is, changes come in, you add a change to the log. That change now for the client is still pending. More changes come in, you add them to the log, and at some point you decide that I have enough stuff in my log, or enough time has passed since the last flash, and then I store that log on disk, and now I can tell all of those clients that yes, your change is now durably stored and finished. So this should also address that question that was just asked on Slido. Won't in-memory buffering affect fault tolerance? And I would ask that as durability. What if the device crashes before change is made in the disk? So you always want your data to be durably stored in the on disk image of the write-ahead log before you acknowledge that to the client. So what happens is, if a change comes in and it's buffered in the in-memory version of the log, and then the machine crashes, what the client will see is that I sent a request and never got a response. So the client would then go and retry that request somewhere else. Okay. So the only case when the client would say, okay, my request is complete, I'll now go on to my next request, is when they would get back that response saying, hey, okay, your change was durably stored. Okay. Now keep in mind that what we're discussing so far is just about a single node. So what happens if we want to store that piece of information on multiple logs, on multiple nodes? When then is the request completed? Yeah. When the log is flashed and carried out the write operation, what happens to the further incoming request? That's a very good question, and it depends a lot on the design of the log. So in some cases, the log is structured in blocks of some kind. So you would, when the time comes for you to flash, is you would lock, or you would make that part of the log not accessible for writes while you flash it to disk. And incoming writes would be added to the next page or the next block of the log. That's one way of addressing this. Okay, and so now these two mechanisms together, the fact that I'm buffering my writes in main memory, I use this write-ahead log, and I essentially batch writes to disk through the log, allow us to get sort of the best of both worlds, right? We don't do random IO because all writes to the log are sequential. We batch these writes, so we don't touch disk for every single update. We touch disk only every now and then. for some definition of now and then. So we seem to be moving in the right direction, right? There's more to this though. So here's another one of these polls. So let me get the poll started on Slido. And the question here is, which of these following designs would you expect to lead to the highest write and read performance? And again, remember that performance here is all about throughput, not necessarily latency, okay? And the options are, when they regard whether we have one random access writer or one append-only writer versus multiple random access or sequential readers. Okay, I'll leave this running for maybe, yeah, a few more seconds, because it seems that the consensus is already reached. Alrighty, I'm closing it in 5 seconds. 4, 3, 2, 1. Okay. What happened? So the correct answer here is D. Okay, one append-only writer with multiple readers. Why? I mean, it's all the things we were discussing so far. You want your writers to be append-only because that leads to higher throughput. You're not doing random I/O, and same for the readers. Sequential I/O is always much better, offers much higher throughput than random access I/O. Okay, so that's what we want to achieve. We want to achieve a design where we have only one writer, for reasons we discussed earlier, and multiple readers that all go sequentially. Right. Flushing. Yes, flushing means, actually, it's flushing with a U. It means that whatever you have in some portion of your memory, you push it to disk, you store it on disk. Yeah. Okay. So I see the time is 12:05. Let's take a quick break, 5-minute break until 12:10 and reconvene. Yeah, just maybe stretch your legs and get something to drink. Okay, good. Let's continue. So, okay, so this is where we stopped. So let's see what an HDFS file looks like. Okay. Typically, you have your file. Like your file is made up of blocks, as we said. These blocks should be stored on data nodes, and then they should be indexed by the name node. You want these blocks to be stored in different data nodes, right? Possibly different. Why would you want to avoid having all of those blocks on just the one data node? Well, the reason is if that data node fails, you would lose all of the blocks of that file, like every single block. So typically you try to, exactly, fault tolerance and parallelism. You try to spread them out as much as you can. So let's say your file has 4 blocks, and these are stored in different data nodes, like data node 0, 1, 3, and 2. Yeah. But then you could go and create more copies of these blocks. And the first replica, and I mean, actually, all 3 replicas of each block should go to different data nodes. Again, for the same reason. If a data node goes down, you don't want to lose all of the replicas of your block. Okay. So this is the first key point here. Okay. And remember that with each block, you compute a checksum and you store that checksum next to the block on every data node. So this block stored in data node 0 has its checksum stored next to it. This copy of block 1 in data node 1 has its checksum stored next to it on data node 1, and so on and so forth. So at a high level, you want HDFS to provide this familiar interface, like a Unix-like file system with the hierarchy of directories and so on. And the API, you expect it to be Unix-like. So you have open and close for files. When you open a file, you get back a handle to the file. When you close a file, you relinquish all of the resources associated with the file. And then given that handle, you can go and read and write data from and to the file. The indexing of your blocks follows closely the idea of Unix-like inodes. And what this means is that your file is made up of blocks, and you have a structure that indexes those blocks, and then you have another structure that indexes your files, and so on and so forth. So there's this multiple layer tree, like this tree structure that indexes everything that goes on some disk in your distributed file system. The namespace is pretty much that I mean, if you've ever used a Unix-like file system, if you're using Linux or Mac OS X or BSD or what have you, you are used to seeing this namespace. So, you know, / is your root file system, and / is also the directory separator. That's the kind of thing you expect to see in a Unix file system. That's the kind of thing you see on HDFS. But HDFS separates file content data from metadata. Okay, so on a single node file system, what would happen is that you would have your inode that indexes your the blocks of the file, and in that file node you would store metadata such as owner and last time of access and size of the file, and so on and so forth. And the actual data would be stored in blocks that are indexed by this inode. Okay, this is the same design in HDFS 2. The data lives somewhere in blocks. The metadata lives somewhere else. And this metadata in this case can be global and local. So per file block, you have, let me see. Yeah, we don't mention that here, but per file block, you have practically two pieces of information. You have a number that tells you how many bytes are stored in the block. That allows you to see whether there are any more, there's any more space left in that block. And then you have your checksum. Yeah. So the blocks and this metadata is stored in the data nodes, and the global metadata, which is the mapping, like the location in the file system, the mapping from file name to blocks, is stored in the name node. So we said earlier that we have only a single name node. So, I mean, someone jumped up on Slido saying, isn't that a bad idea? I mean, why do we have just the one name node? Isn't it a single point of failure? Isn't it a performance bottleneck, right? What is the answer to this question? Why would Google, in all of their wisdom, come up with a design like this? Or to put the question differently, how can we make this design workable? So okay, so someone says we can have a backup for the name node as well. Yes, that is one way to alleviate the name node being a single point of failure. But it's not really the answer to this question, because having a single name node means that that name node is indeed a single point of failure. Yeah. The reason why you want just the one guy is because of that one guy being a single point of contact, as someone says there. So that makes the design much, much simpler. Okay, having only one node keeping all of that information means you don't need to worry about replicating the metadata and keeping that metadata consistent and so on and so forth. It also means you can then spend more time to optimize that metadata, the format of the metadata, to make it more compact, more like easier to access in main memory and so on and so forth. The single point of failure can be addressed by yes, replication or having backup nodes. And actually, HDFS and GoogleFS take an interesting approach to this. We will discuss. But what happens with that guy being a performance bottleneck, right? Because when you have a backup node, you only go to your backup node when your main node has failed. So you still have a single point of contact. Yeah. How can this work? Why is this not a performance bottleneck? It batches transactions, says somebody. Not really. That's not the answer I'm going for here. Or let me put this way. How would the name node, the single name node, become a performance bottleneck? Yes. So exactly. So at least two people got it right on Slido. You make the name node not being a performance bottleneck by taking it out of the critical path. Okay, exactly. So if the name node had to process too many requests that take a long amount of time to be processed, then it would definitely be a performance bottleneck. But you take it out of the critical path. So you only go to the name node to get a mapping from some file to data nodes. And then, that is something that can take a split second. Yeah. And from that point on, when you need to go and read and write the data, which is what actually takes a long time, all of that happens with data nodes. You only talk to data nodes, and then you have too many data nodes around, actually, right? So that's why this is workable, because a name node is made to only store and handle requests that can, it stores data that you can assume will fit in its RAM, and it only handles requests that will take a split second to be handled. So you get someone in that wants to, let's say, create a new file, wants to write a block. That guy will go to the name node and will get back a handle or a pointer to a data node, like that. It takes practically no time for the name node to do it. But then that process would go and spend much more time to store the data, send the data over the network to the name node, to the data node to be stored, right? So how can we find all blocks for a file in HDFS? Okay. Now the name node stores this information, right? So what the name node maintains is for every file on HDFS, this metadata that includes the name of the file, the location of the file or its directory structure. Yes, we'll revisit the single point of failure shortly. So for every file, it stores its name, its location, like in the hierarchy of directories. It stores its file and its file size. It might store more metadata like owner and permissions and times of accesses and so on. And then it stores the locations of all of its blocks. Okay, so that is the kind, like the metadata part of the inode we were discussing earlier. So how can we find all blocks for a file? You go to the data node with a file name and you ask, how did you do that? Like, what will happen is that your client will do an open with a file name. That open is on the client-side library. So what will happen behind the scenes is that the client-side library will send a request to the name node with that file name. And the name node will search through its in-memory image to find the metadata for that file. And then it will return to you a handle, like an ID, right, for the file. Let's say that you then try to do a read, right? The client will issue a read. What will happen behind the scenes is that the client library will use that handle that it got earlier by opening the file, and will go to the name node to ask for locations of the blocks to read. Okay, and again, now the name node that given that handle will be able to locate the metadata right away in its main memory and return to you the locations of the blocks. Okay, and that's also how you can find all replica locations for a block that's stored in that metadata that the name node maintains. Oh, did I lose something here? No, okay. Hello, computer. Okay, so the name node stores this global metadata. So it stores the state of the namespace, which is the set of directories and their files and the hierarchical organization. And what this actually does is it maps path names to unique file IDs. And this is the handle I was talking about earlier. It also stores access permissions for files, modification times, and the locations of the file blocks and their replicas. Okay. For each one of these files, it stores how many blocks, sorry, how many replicas you expect to have, because replication can be tweaked on a per file basis. And so it also needs to store how many replicas you have for every block, not just where to store them, where to find them. This information collectively is called the file system image, right? So the state of the namespace, access permissions, notification times, and the locations of the file blocks. We can call this the file system's image. And this is loaded in RAM for as long as the name node is running, right? When it's booting up, it reads that data from disk in RAM, and then it serves all of the requests from RAM. Why is this so? The reason is as we said earlier, we want the name node to only handle requests that are very quick to be served. Okay, we don't want to go and touch disks because that would take milliseconds. We don't want that. By having everything in RAM, we can serve requests in probably nanoseconds. Okay. There is a snapshot of this image that is stored locally at the name node, and this is called the checkpoint file. Why do we need this? Again, it's for durability and reliability and fault tolerance and what have you. If something happens, let's say someone trips over the power cable of the name node and it shuts down, right? When the name node will boot up again, we want to at least be able to restore its image to a state that was at least correct at some point. And again, here we can play the same tricks as previously with write-ahead logging. So we can acknowledge that something actually happened only after it has been durably stored in the checkpoint file. Now, doing exactly this thing with the checkpoint file might take too long because the checkpoint, and there's nothing in this second line that says the checkpoint file is handled as a log, because it's not, right? The state of the namespace and everything that is in main memory is in some tree structure, so that we can find it quickly. The mapping of names to blocks is probably a hash map plus linked list and things like that. So this structure is not really easy to translate to a log. So we need the log, right? And this is what the journal file is. So the journal file is exactly the write-ahead log for the file system image. It's also stored on the local file system of the name node for the same reasons. A question here one might ask, no one has asked this question on Slido yet, but I'll assume someone has asked the question. Good question, you guy, that you asked the question. Why do we store all of these in the local disk, like in the local file system? Why don't we store the checkpoint file and the journal file on HDFS, like on this distributed file system? Any ideas? So in case of failure, someone says, right, what if HDFS fails? Password retrieve, it's quite small. So here's the thing, right? If you store something on HDFS, it needs to be broken down into blocks and replicated and blah, 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 blah. So what this means is that all of these mutations you do will take time, right? Okay, and you don't want that. You want, as we said earlier, all of the operations that the name node itself carries out to be as quick as you can. So the journal file, you store it locally so that you don't have to pay this cost of going over the network to store the journal. The snapshot is much faster to create locally. And once you have created the snapshot locally, then you can think about going over the network to replicate it. Okay. And as a matter of fact, I don't remember if I have a slide for this. I think I have towards the end. This checkpoint and the journal are replicated. You have backup nodes that store the checkpoint and the journal, right? But you create these backups sort of lazily. So every now and then you would push these updates to your backups. There is a question here to be asked, what happens if the name node fails in that time? And the answer to that is, well, tough luck, right? Here's a question. Is the snapshot of just the local disk node or of the entire file system? The snapshot is of the global metadata. Yeah, the entire the metadata of the entire file system, because this is a single name node. It stores metadata for the entire file system. Okay, and then data nodes are the guys who store the data, as we said. So HDFS sort of writes on native file system of cluster nodes. What this means is that each HDFS block is actually 2 files stored in the native file system, right? Why is this? I mean, what would be the alternative? The alternative would be for HDFS to actually implement a storage on top of a block device. So accessing disk as a raw medium. But that would probably be way more complicated. What HDFS does is it just sees a file system underneath. Like if you run HDFS on a Windows computer, it will store the files on your like VFAT or NTFS or whatever file system. If you run it on a Linux computer, it will store the blocks as files on your X2, X3, whatever file system you have. We said earlier that for every block we have the data and some local metadata, and these are stored like actually as 2 different files. One file is just the content, another file is just this local metadata, which is the checksum and the size. The size being how much information, like how many bytes of the block you've used so far. Okay, now here's the kink. Each block in HDFS is really big. The default is 128 megabytes. Contrast this to the standard size or the typical size of a file system block on a local file system. Like, I mean, most of you are probably using like Windows or Mac OS X or Linux or whatever. Your file system is using blocks of typically 4 kilobytes, 8 kilobytes, maybe give or take. Here we're talking at least 3 orders of magnitude higher, probably more like 5, like 4 or 5 orders of magnitude larger. Why would you need so large blocks? I mean, why does this make sense? What do you think? Yes. If we had a lot of small blocks, there would be more metadata to manage and store. Correct. So that means the file system image at the name node would be much larger. There's another reason. Can anyone think of another reason? I mean, it's sort of related to this one, the one we just mentioned. Any ideas? Someone says performance. Can you elaborate a bit? Faster transaction, minimize cost of SIG. Not really. Flexibility. Well, someone is going in the right direction. Says, because of network transfers, you want to fetch larger blocks. Read more data as blocks are bigger. Yes, so I'll write on this. Okay, I'll use this to go to where I want to go. Every time you try to read or write something, remember how you need to go through the name node to get the location of the block. Yeah. So this means that for every IO you do to a block, you need to pay this sort of overhead of going through the name node. The fewer times you go to the name node, the lower that overhead is, and also the lower is the load that you put on the name node. You also, I mean, and what this translates to is you don't need to access that many blocks, as someone says on the slide. Okay, but this is also about making better use of bandwidth. Okay, because once you have the location of your block, and let's say you try to write it, you can stream the data in one TCP stream. If you have to break it into more blocks, you would need to pay the overhead of connecting to the data nodes more times, and then you would be breaking this high throughput stream into smaller requests. So all of these reasons, I guess, were mentioned in the slide, and all of these reasons are why HDFS blocks are so big. Okay. Someone said that it's to reduce seek time. It sort of it's not exactly incorrect, because having larger blocks means you have fewer blocks to index, meaning that seeking to an arbitrary block would probably take lower, like less time. But the gain you get from that is actually offset by the fact that you now need to go and seek within this much larger block. Why not make NTFS or FAT32 blocks bigger? What's the effect of that in such file systems? Excellent question. And the answer to that is, how do these systems treat their blocks? Okay, typically the block is a unit of allocation. So if you create a file, an empty file, I mean, not necessarily an empty file. If you create a file and you store just 1 byte in that file will take 1 block on disk. Okay. So if every single file you had on your computer took up 128 megabytes minimum, then that would be a disaster, right? You would run out of space very, very quickly. Right. So you don't want that on a typical desktop or laptop computer. Most of the files there are very small, and only a few files are very large. What is a placeholder in the slide? I thought we mentioned that last time. Maybe we didn't. So for every lecture, the slides come in 2 versions: pre-lecture and post-lecture. And there are some quizzes, like some questions, some parts of the lecture that I would like us to discuss. And I want us to discuss it by not assuming you don't know the answer. So whenever there is something like that, there is a placeholder slide in the pre-session reading material, because in the past, people wanted to print out the slides and then write on them, take notes as we go. So by allowing space in the lecture material, they had somewhere to store, like to write their notes. After the lecture, the file will be updated with the complete one. Okay. So we're talking about the HDFS block size now, but someone said, why don't we have such huge blocks in NTFS or other local file system? And in that case, this is the answer why. Why can't you use half full blocks on NTFS? Because then that would mean that your blocks are just a collection of smaller blocks. If you can have half full blocks, right? Because the file system would need to keep track of, out of this big block, I only have used so much and only take so much on disk. That sort of defeats the purpose of having blocks. Okay. HDFS had some way to deal with a large block space wastage. Yes and no. In most cases, the space you waste is only in the last block of every file. And typically your files are big enough to have way many blocks, like a sufficiently large amount of blocks, where if you just waste some space in the last block, that's not a big deal. Okay. Someone asks if I can provide notes for each week's topics. I can look into it. Yes, I can look into it. Are snapshots the only thing stored in the checkpoint file? Yes, and we'll get back to that soon, because there is a kink to it. Any possibility of offline lectures in future? I would love to. I don't know though. I mean, Omicron is quite quirky. Okay, let's move on. So assuming now you know the location of all of the replicas of a block, what is the best way to read the block? Is it to contact all replicas and return when the first one responds? Is it to contact a replica chosen uniformly at random, and so you balance the load? Or do you want to contact a replica that's closer to the client? Or do you want to contact a replica that's less loaded? Right. Let me see, do I have a poll for this? No, I don't. Good. Good. The reason why I don't is because this is a trick question. Okay, it's a trick question. All of these options work, actually. But what happens is that each one of these options optimizes for a different use case. If you want to contact all replicas and return when the first responds, you try to optimize for latency. Okay. What you do is essentially you put more load on the network because you send out more requests, and you put more load on the data nodes because now more of them are working to serve your single request. But when the first one comes back, that's the only answer you care for. The other answers can come in later on and you will just ignore them. But this means you will have the lowest latency you can have. Okay. If you go with the second option where you contact a replica chosen uniformly at random, this optimizes for load balancing. So every time you go to a different replica, this means that the load is spread across all of the replica nodes uniformly. C, where you contact a replica that's closer to the client by network distance, again tries to optimize for latency and also for throughput, okay? Because closer, remember, means that it's probably, you try to find a replica that is in the same node as you. If not, then in the same rack as you. If not, then in the same neighborhood at the second level of this hierarchy, and so on. This means that your latency will be smaller because you have fewer hops to do, but also that there is this possibility for a higher throughput because the probability of more guys hitting the same area of the network is lower. Okay. And D also tries to optimize for load balancing. You want to contact the replica that's less loaded so that you don't overload any single replica. What's the difference between A and C? Like both of these optimize for latency. Someone asks if this read policy is configurable. Actually not. There is a default policy used in HDFS. So what's the difference between A and C? They both optimize for latency, but A puts more load on the data nodes. You go and contact all of them, whereas C will only contact a single data node. It's not guaranteed to offer you the lowest latency. A is, right? But C goes a long way towards actually getting lower latency and better throughput. And we can also discuss B and D, like they both try to optimize for load balancing, as we said. Yes, exactly. A wastes a lot of bandwidth and processing power. Yes. So B and C both optimize for load balancing. The main difference here being that B and D, that D requires you to either contact all of the replicas to see which one is the least loaded, or to have that information stored somewhere, let's say that the name node, so that you can go to the name node and get that information. Whereas B tries to achieve this in a probabilistic manner. So no guarantee that you will hit the least loaded replica. Okay. Assuming the A policy happens in big scale, would it not result in more latency due to network load? Yes, actually, yes. That's correct. That's correct. So HDFS and GoogleFS actually have gone with C, right? Because C doesn't overload the network, and does go towards this lower latency and higher throughput, even though it cannot guarantee that. Okay. And this is a high-level view of how HDFS feeds work. Like your client has a file name. With that file name, it goes to the name node. The name node responds by the handle. Given the handle, you can then go back and get block IDs and locations of block IDs. You get them back to the client, and from that point onwards, you go and read or write data, read in this case, directly from the data nodes. Okay. Now, for this to work, there needs to be this cluster membership protocol or layer. Okay. What happens here is that each one of these data nodes need to somehow update a global state saying that I am here, I'm alive, I'm working as expected. And then the name node can also inspect this global state to see which of the name nodes, which of the data nodes are still up and running, and so on and so forth, right? So where is this global state stored? It's actually in the name node, right? And here we can also see the secondary name node. This is sort of the backup. Yeah. Yes, there is a secondary name node here. This is the backup name node. You never go to the secondary name node to serve a request. You would only go to the secondary name node if your primary name node fails. Good question here. If a file is less than 128 megabytes, let's say 2 megabytes, and the file is stored in HDFS, what would be its size in HDFS? And what about the block size of it? That's a very good question. What do you think would happen? Remember, these blocks are not actually blocks on the disk. They are files in the file system, right? So these files, these are 128 megabyte files, potentially, but that is stored on a file system where the block size is like 4 kilobytes. Okay. So the question is, I mean, what I think your classmate here wants to ask is, would the block size always take 128 megabytes, or would it start by being smaller than that and then grow up to 128 megabytes? And the answer here is not straightforward, because HDFS is an open source implementation of the Google FS. There are many, there are quite a few implementations of the Google FS design out there, right? Not just HDFS, not just the Apache Hadoop DFS. There are many implementations of HDFS, to say so, and they take different stances at it. Okay. Yes, it depends on the local file system as well. So even if you tried to store the whole 128 megabytes, there are file systems where if you have sparse files, like files where you don't have any data stored for some part of the file, then that would not be allocated on the disk. So it's a bit complicated to answer this question, but it's a very good question. How does the update between name nodes work? So what happens is that you have this journal and you have this this image, right? Someone asked earlier whether I can reconstruct the image given these two, and the answer is yes. You load the checkpoint file, and then you replay the journal on top of the checkpoint file, and that gives you the final correct state as of the last update of the journal. Yeah. And again, these are designs that come from databases. So typically, if you have a replicated database, what you do is you create a copy of your database at first, and then every time you do an update, what you send to the remote nodes is the logs. You do this thing called log shipping. Yeah. And this is the idea here again, because what happens is that the name node pushes its journal to the secondary name node every now and then. Okay, so every now and then, this guy has an up-to-date journal, and it already has a checkpoint processed in the past. But given that checkpoint and all of the journal entries from that checkpoint onwards, it can reconstruct the current state. Is the local data node's block size 128 megabytes? If you mean whether the size of the blocks in the local file system is 128 megabytes, the answer is no. The block size of the local file system is whatever the size of the block of the local file system is. If you run this on Linux with X3, it will probably be like 4 kilobytes or 8 kilobytes. Okay. All right. Okay, so this is how reads work. When is the best time to check the block checksum, and who should do it? The options being A, the data node right after the checksum is computed and stored. B, the name node right after the checksum is computed and stored. C, the data node periodically, or D, the client when it reads a block. Okay, so remember, every block has its checksum stored next to it, and checking the checksum requires that you read the block, compute the checksum over it, and then make sure that whatever you computed is the same as what is stored in the checksum file. Okay. B here should be out of the window right away because you don't want the name node to do any data intensive stuff. Okay. So the answer would be one of A, C, and D. A and C have the data node do this action, and well, in the A case, if the data node computes the checksum right after it's stored, well, chances are the check will succeed, right? And for C, chances are the check will also succeed. The problem with C is that by doing it periodically, you might lose something. But believe it or not, the correct answer here is either C or D. So with HDFS, whenever a client reads a block, the client will also read the metadata, and the client will do this check. And if the client sees that the two checksums do not agree, then it will inform the name node that a replica is wrong. Yeah. The data node can do it periodically, and by doing it periodically, as we said, you might be missing stuff, but at least you're not making this check part of the critical path. Okay. So both C and D work in this case. And then writes that are the tricky bit here. What is the best way for a client to create or write a replica? There is this plot. I'll enable the plot. Also, I will just probably go ahead and explain what the answer is. So there is the, sorry, not poll. There is a poll on Slido if you want to go and have a try at it, why I explain here. So what's the best way for a client? Should the client contact all replica locations in parallel when the client wants to write? Should it contact all replicas one after the other? Should it send to the first replica and then create a chain where that replica sends to the next and to the next and to the next? Or should the client send to the first replica and then lazily create the other copies? Okay. So I see in the poll, nobody has gone for B, as in client contacting all replicas one after the other. I mean, that's interesting. I'm not sure why you've gone with that. I'm guessing or suspecting that the reasoning goes that this would take probably too long. So there must be something better than this. A few people have said that the client will contact all replica locations in parallel, like broadcast or multi-unicast. That's not a bad option, but there is a problem to it that we need to understand. A few people have gone for D. So the client sends the data to the first replica and then forwards to the remaining replicas lazily. Excuse me. This seems to be a fairly popular, like it's the second most popular option so far. but it has a problem. The problem is, when do you assume that your write has succeeded? If you assume the write has succeeded after only the first replica is created, what happens if that replica fails for whatever reason and your client fails before creating the additional copies, right? So this means that your data is now lost. You probably don't want this, okay? The correct answer here is actually, is actually C. PowerPoint is acting up. So the correct answer is actually C. But why is that? It's a very subtle point. And to understand this, we need to go networking mode again. Apologies, whoever said we shouldn't do networks in this course. So at the end of the day, if you need to create these 3 copies of your block, you need to transfer 3 times the size of the block bytes over the network. So you can either do it in parallel, or you can do it one after the other, or you can do this chain, okay? So A or B or C. What is the problem? The problem is that, so people say that both that A and B take up a lot of traffic. And I will actually say that the amount of, let's say, bandwidth used cumulatively across the cluster is the same in all 3 cases. In all 3 cases, you copy, you transfer 3 times. I mean, if you do 3 copies, 3 times the size of your block. The difference is elsewhere. So what happens typically is that every node has, 1 or more network cards connecting it to your cluster. Suppose it has only 1, just to make this simpler to discuss. That card connects to the top of rack switch through some cable. When the card is enabled, when the interface is brought up, it negotiates its let's say, connection mode. And typically what you have in these cases is that you have a full duplex channel, meaning that your card can send, I mean, if the connection is, let's say, a 1 gigabit connection, a full duplex channel allows you to send data at 1 gigabit per second rate and also receive data at 1 gigabit per second rate, okay? But there is this upper limit. I mean, if your card and the connection is a 1 gigabit per second connection, you can only send up to 1 gigabit per second. If you try to do the broadcast or actually the multi-unicast, right? This means you connect to 3 nodes concurrently, and you send out the data to those 3 nodes concurrently. Think what that translates to. Like, the connection to each node is only 1/3 the bandwidth of your maximum, okay? And this means is that the time it takes to create all of those 3 copies is 3 times the time it takes to create 1 copy. That is also the same with B, right? Because if you create the first copy, you wait until the first copy is done, then you create a second, then you create a third. Each one of these copies happens at full speed, but the time it takes to create all 3 is 3 times the time it takes to create 1. But by using this chaining in C, you can create your first copy at full speed, right? And then the data node that receives that first copy can start sending it to the next node right away. So while the data of that block is in transit, like in flight to the first data node, and it arrives there, as bytes arrive, that first data node can start sending those bytes to the second data node. And the second data node can start sending those bytes to the third data node. So taking a step back, you can see that all of these transfers happen at full speed, right? You send out at full bandwidth your first copy. The data node sends at full bandwidth to the second copy and so on. And the time it takes to create all 3 copies is quite close to the time it takes to create 1 copy at full speed, okay? So that's why C is, I mean, I won't say the correct answer, but C is what HDFS and Google FS have gone for. I'm not sure what happens here. Okay, good. So this is the process we were just describing, and there are some added tricks to it. So the time is now 1 p.m. So we should finish this lecture. There's a couple of things more to discuss. As a matter of fact, let me see. I think there's maybe like 2 or 3 slides more. Hello. Yes. So instead of using the lab slot to cover this, what I'll do instead is we'll cover this next week. Okay, we'll cover this next week. So no labs this afternoon. No lecture this afternoon, and we'll just continue next week. Okay. There's a couple of questions on this right thing and the algorithm. Good questions, all of these. What I would suggest is that you either post these questions on the forum or ask me next week. Probably best to post them on the forum so that I can go and explain to everybody. No lab, but you need to do the Spark setup for next week. It shouldn't take you long. You don't need to do it today. Just do it whenever you have the time. Okay. Good. And the situation with the Web Science Lab is being looked into, as I said. I'll let you know what the outcome is. Notes for lectures, I'll look into it. Yeah. Okay. Good. Thank you, everybody. Have a nice day. And cannot access the forum on Moodle. Okay. Can you send me an email or talk to me on Teams, and we can look at it together? Oh, it's hidden. Shouldn't be hidden. And I will extend the quiz. Yes, I will extend the quiz right now. Okay, guys. Thank you, everybody. And
thank you, Professor.
Thank you, Professor.
Cheers.
Thank you, Professor.
Thank you.
Thank you. Bye-bye.
Thank you, Professor.